So I decided to do a problem from the book that's in the beginning of 15.2 because some of the students at Starbucks were asking me questions and they were using the answer key, and the answer key is shit, and it's teaching the actual wrong shit to do. While it might have worked, it's not what they were supposed to be doing. So we want to find f dot dr along the line segment from p going from -1, 0 to q going to 6, 0. For our force, oh, I didn't put my vector over it, -8x and 3y. So a way to go about doing this is we need to make a line from P to Q. And it's clear that -1, 0 and 6, 0 is a horizontal line. But I'm not going to let that sway me because I'd rather go over and do how you do it in any way, shape, or form. We're doing 1 minus t times r0 plus t times r1. This will give us any straight line. And we can use points as vectors, but not all vectors are points. Keep in mind that the vector can be put anywhere, but any point can be made into a vector just by making an arrow that goes from the origin to it. So I've got -1, 0, and I've got 6, 0. And we're doing 1 minus t times the first part plus t times the second part. For my r, I'm getting, for the x component, I'm getting -1 times this is t minus 1. And then I have plus 6t. That's my x component. And my y component is 0, and 0 is a total of 0. What do we have there? We have 7t minus 1, 0. That's my r of t. So we need dr. So what's the, I mean, that's what we were setting it up for. So dr will be, and recall it's with respect to t, 7, 0. When we set up line segments this way, t goes from 0 to 1. You can always verify it by plugging in 0 and plugging in 1 and seeing if you get back the initial points. If I plug in 0, I get -1, 0. That was my P. And if I plug in 1, I get 7 minus 1 is 6, 6, 0. That was my Q. Okay, so we need f dot dr. What's f dot dr? F was -8x and 3y. And we're dotting that with 7 and 0. And we get -56x. So along the curve, we are using, it was parameterized with t. F dot dr 0 to 1. We have -56. I need it in terms of t. X along that path is 7t minus 1. Then we have dr dt. We already did that part. Dt. So we've done the f dot dr. We've got our dt. Shit. I didn't realize this problem had big numbers. Where's my calculator? Wait. 350 and 42 is 392. I don't need a calculator. Quit being a wuss, Jones. -392t plus 56. All right, so I've got that number divided by 2 is 196, negative 196 t squared plus 56t. Evaluated from 0 to 1. I got negative 196 plus 56 is negative 140. Let me get the instructor thing up to that point.
Yeah.
So the answer key gets negative 140 also. But they went from negative 1 to 6. They did I don't know what the hell they did. They came up with their own funky wonky thing, despite teaching it a very specific way, doing an easy, convenient way to do it. They did not shift to DT. Well, they did. It says DT right there, but this is not T. They parameterized T in a different manner. They did not do what we were doing. So like, and that's how 7 through 10 is. I didn't check the other ones. So if you see some wonky stuff, like they do something weird in the answer key, don't spend 6 hours trying to figure out why your answer is different. Send me a message and go, is their answer right? Or is their process right? Because they got the right answer. Their process is different than what's being taught. Some grad student did this, and they always have grad students make the answer keys, and they just use their own intuition on math and didn't follow the procedure, which is a bad idea. All right, so
Obviously not smart enough to teach.
wait, what?
They're gonna just make them static smart people.
Oh, okay. So some people are wondering, why are we doing DS, and then why are we doing DX, DY, and DZ in some of this shit? Why is F.dr doing DX and DY, and when in the first part of 15.2 we're doing DS? So here's why. Sometimes we just want the line integral, and we're not in a vector space. We're not in a vector field. So like the line integral, we're just finding the value along a curve. It might have a density function. It might have a temperature function. We might be integrating something along that. And then the reason why we went to the whole F.dr, where, you know, it's F.dx plus G.dy plus H.dz. Well, our vector fields, we do vector fields in terms of X, Y, and Z components. And so the effects of vector fields on things within them have to be dealt with in that manner if we want to keep things easy. So like, this is a vector field, and to deal with the components, we do this. We do this. DS isn't as helpful. DS is less helpful. So that's why we're learning two different ways. The DS is when we're not in a vector field. This F.dr is when we are in a vector field. Okay. So speaking of that, let's do something in a vector field.
Already in the vector field.
So this is from the book. I have not looked at the answer key. I have no idea if they did it right or wrong. Is a unit, well, I said square. That is not right. That is a unit cube. So it hits Z at 1, it hits X at 1, it hits Y at 1. And the path along is starting at the origin. It's coming out to this point right here. It's going up to this point right here, and it's going back to the origin. So maybe I'll call this P, Q, and R. And I might even write it sideways, viewing it as a triangle. Like that. That would be P, Q, and R. It might make it a little easier to work. It's not X, Y because the values are different. P is the origin. Q is along the x-axis one, along the y-axis one, but nothing along Z. And R is exactly 1 unit in Z direction up from Q. So we're effectively making a closed loop. So if I call going from here to here curve 1, and here to here curve 2, and then from R to P, let's call that curve 3. I can treat my curve as 3 pieces. A piecewise smooth function. All right, let's look at each of these. Let's do along C1 first. Let's make our R vector. One minus T times my initial point or initial vector plus T times my second vector. And we can see the first part is 0. So R of T is just T, T, and 0. Which means dr dt is 110. Which means that's my dx, that's my dy, and that's my dz. If I write this at, I don't want an equal sign there. There we go. Dr is 110 dt. So I know the x component is t, the y component is t, the z component is 0. Let's substitute that back in to our function. Our curve was, I'll rewrite it down here so it's visible again. I just keep fucking up. So z equals 0 and dz equals 0 kills this term and it kills this term. That's handy. My curve is only one component. And we're going from 0 to 1 for t. We've got the negative sign, y is t, and then x squared, x was t. And dy is 1 dt. So that's this right here. Parameterized in terms of t. So what I have, I've got negative t cubed, the integral from 0 to 1 of negative t cubed dt. I'm gonna be able to fit this all on one line, not have to use as much room. So we integrate that, we've got negative 1/4 t from 0 to the 4th from 0 to 1, and we just get negative 1/4. I'm going to come up here and replace my C1 with that so I don't lose that piece of information. Actually, Lawrence said don't rewrite over things like that, so I'll write it over here. I'll start keeping track of my C value up there. We all good with curve 1, which is P to Q. So that was C1. Now we're going to do C2 and C3.
I'm a little confused on how dr, like the dr, how is the x, y, how is that just dx, dy, and dz? I don't get that first.
Because R is a function of X, Y, and Z. dr has always been dx, dy, dz. That has never changed. Component wise. We've been doing that since the beginning.
Okay.
That's it. That's it.
If it makes you feel better pictorially, look at it pictorially. In fact, I'll use that triangle we have over there. My dr, nope, I don't want to use the whole triangle. Just one vector. I've got some point over here, and we're going along an X length, a Y length, and a Z length to get to it. So this is R. That's the R vector. This is the I component of R. I's component. This is the J component. And that's the K component. If I were to treat this as a dr, the same thing has to happen. There are little steps in each direction. So rather than it being let's just pretend we zoomed in so I don't have to try to rescale this. This is a really fine, small dr segment. I'm still going to have a section that goes dx. I'm still going to have a section that goes dy. And I'm still going to have a section that goes dz to get to it. Because they are the R vectors to any point, and these are small steps in the X, Y, and Z direction. And so we use D for those. So dr is dx, dy, dz. Does that work for you?
Yeah.
You sure?
Yeah.
Okay. It might be easier to think about what you would do in 2 dimensions and y, dy, and dx. Because y is a function of x. When we do dy, we go a small portion in x. All right, so that was curve 1. So let's put a little line in and look at curve 2. Curve 2, we're going from 1110 to 111. It looks like the only motion is in the z direction. Like if I would do it, this is 001, the difference. But let's see what that is in the R. I'm starting at 110, so I've got 1 minus t minus, not plus, 1 minus t times 110 plus t times 111. So I've got 1 minus t for the x component plus another t from the R1. That's my y, my x, and that's my x. This is my y. Y is 1 minus t times 1, so 1 minus t. And then from R1, we've got plus 1t. And then z has a 0 plus t. So I am getting 1 t, that's my r. So dr is going to be 0, 0, 1. Again, dx and dy and dz. So my dx and my dy are zeros. The only term I need from that integral up top is the dz one. And dz is just 1 dt. So I integrate this, I get 3t evaluated from 0 to 1, and I get 3. And that's for C2, so I will list that up top as my C2 component. Looks like I'm going to need another whiteboard. That's all right.
Why do you write in the school? You got a 3.
What?
Your C2 is 3. Why you write 2?
I still can't hear you. Brandon, what is he saying?
That's the curve. Why he write a 2 over there, out there, and he got an answer.
Because I'm a fucking tool.
Oh.
I had C2 in my head, and so I wrote the T from C2. That's what I should have wrote. Good catch.
I'm like, where did he write 2? I don't see a 2 down there anywhere.
Great catch. Yeah, that was me being a tool. No, I was testing you. Isn't that right? What Redden says? I was testing you.
Yeah. Right.
Rather than just admitting to making mistakes.
He's like, all right, what did I do wrong?
God forbid a teacher make a mistake. All right, I'm going to recopy this equation, the integral onto another board. I'm going to recopy our C1 and C2 so far. And C equals C1 plus C2 plus C3 is negative 1/4 plus 3 so far. And we are on the final component. And the final component goes from R at 111 to back to P again at 000. And so this is our C3 path. That's the prior information that we had. That's the function or the integral that we're looking at. So let's just do our C3. Let's figure out what RT is. RT starts at 111. So we've got 1 minus T times 111 plus 0 times, or I'm sorry, plus T times 000. So R of T equals 1 minus T for each component. So dr is going to be -1, -1, -1 dt. Again, dx, dy, and dz. All right, so this is going to get fucking ugly. Because everywhere up there, nothing oh, that's a Z. Nothing disappears. And every letter that isn't with a D with it is a 1 minus T. So let's look at our curve. We're going from 0 to 1 for all of them. X squared would be 1 minus T squared. And then Z is 1 minus T. And then dx is -1 dt. And then I've got minus y, which is 1 minus T. And then x is 1 minus T squared. And dy is -1 dt. Oh, that actually might cancel out. I know I still got to do the dz, but I want to see if this cancels out. This is 1 minus T cubed. I'm going to put the negative sign out front. That's that component. Here I've got two negatives. I got a plus. I got a 1 minus T cubed here dt. Look at that. Oh, that's beautiful. Those are going to wipe out. So the only part I haven't listed, those will add to 0. We also need the rest of it, which was the plus 3 dz, which is -1 dt. So this is all one line, the blue stuff. And it cleans up to 0 to 1, -3 dt. So I got -3t from 0 to 1, which is -3.
It might help if you put a negative before it.
Fine.
No,
So
I'm sorry. I might not comment on it if I didn't think you might just put 3 in your answer anyways.
I would have. All right, so we got our curve up there. Our curve, those aren't actually our curves. This is the integral for along those curves. That's what the C means. So the integral along the C equals the integral along C1 plus the integral along C2 plus the integral along C3. That's -1/4 plus 3 plus -3, which we just found. So the entire integral was -1/4. I thought that was going to be some ugly, ugly calculus that we had to do. Look at that, cleaned up nice and neat.
That calculus for you either
That's
turns
a
into
book problem.
a slog or cleans up really nice.
That all depends on whether it was designed for a textbook where they like to sugarcoat everything and make it easy, or if your scrub teacher does it and just wings it and throws some numbers at you, and you never know what you're going to get.
Get imaginary.
Am I right or am I right?
Oh, man.
All right, so line integrals, we're basically doing the DS version. DS version when we are not in a vector field. Doing some operation, something in a vector field. And we use dr, or particularly f dot dr, in a vector field. And that is an integral. That sure looked like an apostrophe. So let me clean it up a little bit. Now I want to look at 15.3 a little bit. We've got conservative vector fields here. You guys ready?
Yeah.
All right. So we want to find out if f is conservative, and if so, find the potential function. I suspect many of you did not watch the video for that yet, because they went up this weekend. If we want to see if something is a conservative vector field, the curl of f needs to equal 0, the vector, or effectively, when we do the 2D version, that rotation of f needs to equal 0. And so these are both 2D. Most of the stuff we're going to do, at least in this section, is 2D, just because it's easier to work with. We will do some 3D stuff. But the 2D version was ddx, ddy, f, and g. The 3D has got your whole ijk, ddx, ddy, and ddz, f, g, and h, where the f, g, and h are components of the force field vector. So f, g, or f, g, h. So we can work out that one later. I also did it in the video. This one, you're just finding the determinant. That's a linear algebra term. The determinant of this is just the way we've been doing cross product stuff. The diagonal, first diagonal minus the other diagonal. So dg dx minus df dy. We need that to equal 0. If f is conservative, dg dx minus df dy equals 0. Now, in the lecture videos and in the book, they solve this and they say dg dx equals df dy. And I did too. I put that in the lecture videos. I'm going to encourage you to not do that. I'm encouraging you to stick with this. Because if you stick with this, Green's theorem is going to be really fucking relatable. Green's theorem uses dg dx minus df dy. So I wouldn't use that. This is also in Green's theorem, which is the next section, 15.4. And that's when it does not equal 0. So we'll get to that. Stick with this format. You can use either, but if you want to like really make it easier for yourself. So let's take a look at what we're doing. We had a f equaled x ln y, y ln x. This is my f and this is my g. So dg dx is ddx y ln of x, which is y ddx of ln of x, which is y over x. The only reason I did that out the long form is because some of you were making mistakes on the derivative of ln of x so far this semester. Like anything that wasn't a polynomial, some people were just fucking up the derivative. That looks like a 2. I want to rewrite that to make it look like a d.
Don't worry, we all sometimes mess up on polynomials.
So let's look at df dy. ddy of x ln y. So dg dx minus df dy is y over x minus x over y, which doesn't equal 0 unless we're at like 1, 1. But that wouldn't be a conservative vector field. That's just that's just a coincidence at a single point. For in general, it does not equal 0, so f is not conservative for a. So no, f is not conservative. And I will write down the other problem on another tab real quick.
We said math had to be free of politics. Now we have conservative vector fields. Hey, Mr. Jones, where are our liberal vector fields?
What?
Where are the liberal vector fields? We have conservative vector fields. Where are the liberal ones? What about the Republicans and the Democrats?
I'm ashamed to have you as my SI.
Okay, I wasn't the one that come up with it. I'm
Whoever
just
came up
spreading.
with that, no. Just no. Shut it down. Terrible. All right. So let's take a look at the other one. That's my F. And this is my F and my G. So let's figure out what dg dx is and df dy. Well, I've got a negative there. And the derivative of this with respect to x is 1. I guess I don't need 2 lines for this. Because if I do the derivative of f with respect to y, no one gives a shit about the 3x. No one gives a shit about the 1. The derivative of negative y is negative 1. So these are equal, but I told you to do it as subtraction, or encourage you to do it as subtraction. Negative 1 minus negative 1 equals 0. So yes, this is conservative. And I asked you to find the potential function. So let's find the potential function, and I'm going to motivate y. Since I'm running out of time and I want to get it done now. For a conservative vector field, the integral with f dot dr is phi at p1 minus phi at p0. It's like the fundamental theorem of calculus. But I don't think I have it in words f dot dr. Let me make sure I'm giving it to you in the same format. Yeah, I did. F dot dr. Okay, good. So that's why finding the potential function is easy, because it's, or helpful, because it just solves the problem. If we wanted to integrate this. So let's find the potential function. Recall, for a potential, if f is a conservative field, it equals the gradient of some potential function, which is d phi dx, d phi dy in this case. Are you laughing at me, Brandon?
No.
Did I do
I'm
something
not.
wrong? Okay.
No, you didn't do anything wrong.
You just having a
This
stroke?
class,
What's going on?
this class is the one that's wrong. This class is the thing that has a problem. That's all.
Are they talking shit about me under their breath? I'll give them all F's. You just let me know. Everyone right now, including James. I don't give a shit if his dad's a teacher. No, I wouldn't do that. That would get me in trouble. All right, so if this is the case, d phi dx has to equal my f component. And my d phi dy has to equal the other one. Negative x minus 4y minus 2. If I distribute the negative.
Oh, that's fees.
All right, so I'll start off, I'll integrate the d phi dx. Let's integrate this with respect to dx on both sides. And I get phi of xy equals 3/2 x squared minus xy plus x plus some function of y. I used f and g above. I'm going to use h right now. Now, if I take the derivative of this with respect to y, I should get this. So let's do that. d dy. d dy both sides. So the left side is d phi dy. That's easy. The right side, I get negative x plus h prime of y. And that should equal this. which means if I add negative x to both sides, I have h prime of y equals negative 4y minus 2. And if I integrate this with respect to dy, I should get h. Negative 2y squared minus 2y. So my phi of xy, I had 3/2 x squared minus xy plus x. That's what I had above. And now I have my hy components are negative 2y squared minus 2y.
Yeah, we should have. No, I know what you're talking about.
I'm saying what happened, like, is an indefinite,
Oh.
have like some constant. So it has to do-
Hey, Mr. Jones,
Yeah,
that's the H.
some of the class is wondering why you didn't add a plus c at the end of your indefinite integral. Never mind. There wasn't a deep reason for it.
that's true. There could be a constant with it. The constant tends to be not used because the reason why we come up with potential functions is to use them. So if I were to do this problem that we just had, if we treat it as an integral, I'm gonna rewrite phi down here. If I want to evaluate this integral from 0 or negative 1, 2 to 0, 1, this was my f, and I've dotted with dr. So that is f dot dr. And we know f is a potential function. I should be able to do the integral as phi at p1 minus phi at p0. So P1 is 0, 1. I'm going to do phi at 0, 1 minus phi at negative 1, 2. And here at this point, you're just plugging and chugging. So if you got to go to class, I would bounce. We're just plugging this shit into that one. So phi is 0, 1. Anything that's got an x in it is a 0. So 0, 0, 0. I've got negative 2 times 1 squared minus 2 times 1. I'll put plus c back, and I got plus c. So this is negative 4 plus c. And if I do phi at negative 1, 2, this is not as quick, but still doable. We've got 3/2 times negative 1 squared. And then I've got minus x. X is negative 1. Y is 2. Then I've got plus x, so plus negative 1. Minus 2 times y squared is that. And minus 2 times y is that, plus a c. So what do we have? I've got 3/2. This is plus 2 minus 1 minus 8 minus 4 plus c. So let's see, the 2 and the negative 12 make negative 10, negative 11. Plus 3/2 would be negative 9.5 plus c. I'm assuming I didn't mess it up. I'm trying to go a little bit quick because we're out of time. I've got -4 plus C minus -9.5 plus C, which is -4 plus C plus 9.5 minus C. Notice the C's cancel out and we're just left with 5.5, which is 11/2. So if you have the potential function, if you're doing f dot dr along several things, in a conservative vector field, this had to be conservative. This is the shortcut to getting the solution. We will be spending a lot more time on 15.3 tomorrow. This was just to get you warmed up. I will see you guys tomorrow. Have a good day.
I'll be holding my regular SI hours later today as well.